Hey guys, welcome back to Bayesian. We're starting a new unit, and in this unit, we'll be sort of disavowing ourselves of treating everything as a normally distributed, all outcomes as a normally distributed variable. So you may have noticed that at least up until your second homework assignment, we've been treating a lot of things on the logarithmic scale because that helps with the approximate normality assumption. A lot of things in this world, binary data, for example, well, actually, counts, binary outcomes, some number of successes out of some number of trials, things with special zeros. All of these things are not going to be approximately normal, and so we need a different tool. The saying, if all you have is a hammer, then everything becomes a nail. We've been sort of treating everything as a nail, but making and taking a natural log of all quantitative variables thus far. The natural log thing works if our outcome variable is right skewed. It tends to work, but it certainly doesn't work for a lot of cases. So what's the big idea? Okay, this has been our world to date. We have a linear model. So we specify priors for the intercept, all the coefficients, and our sigma standard deviation. And because we simply take this mean and plug it into a normal distribution, the mean is allowed to be anywhere from -infinity to infinity. And that's because the normal distribution is defined between -infinity and infinity. But once we start dealing with things like counts and binary data, this -infinity to infinity shenanigans are not good for us. If we have binary data, and we're dealing with probabilities, clearly those have to be between 0 and 1. If we're dealing with counts, not only do they have to be integers, 1, 2, 3, 4, 57, they are also bounded below by 0. So what we need to do is we basically take our linear model, and we assign it to some function of whatever parameter we're interested in. So I'm trying to be very general here. So theta here is a general parameter. We basically take our linear model, and this is actually the linear predictor, it's called. Linear predictor, and we feed it through a special function called a link function that keeps our parameter values legal. When I say legal, it must be between 0 and 1 for probabilities and proportions, right? This becomes a pi for probability. So we take our linear model, we feed it through a special function called the link function that ensures that no matter what the combination of various alphas, betas, and x's, our probability never exceeds 1 and never gets below 0. And this is true also for binomial distributions. For Poisson and also negative binomial, well, this is just, it's all right, it's just not gonna work. That should say negative binomial. We need to have a function such that our alphas and betas and x's can be anywhere from -infinity to infinity, but have a link function, that special function, that ensures whatever we feed into this distribution is greater than or equal to 0. So we take everything we learned, the linear model, by the way, the link function for the models that we've been dealing with thus far is called the identity. Why is it called identity? Because we don't do anything. The function is don't do anything. We make our linear combination of alphas and betas and x's that can be between -infinity and infinity, and we simply, as is, without any further transformation, plug it into a normal mean. On the bottom, we take our linear combination of alphas and betas and x's, feed it through a special function called the link function, and then through this inverse link function, plug it into the various distributions. on the legal scale. So a little bit more precisely, and I'm specifically keeping the probabilities and proportions and counts on the same slide, because I don't want you to think that there's anything special statistically about dealing with, at least not in the GLM, Generalized Linear Model sense. It's nothing, all that special and different between counts and probabilities and proportions, other than the special function that we use. So let's deal with counts first. Here is our linear model. Linear combination of alphas and betas and x's, can be anywhere between negative infinity and infinity. We assign it, equate it to the log of something. And then that means if we exponentiate it, we get, we put our linear model, the entire thing, into the exponent, and then we simply feed it into a Poisson distribution. So you can see if we have e to the negative infinity, this is basically 0. And a Poisson of 0 is defined. Poisson of 0, the largest mean count is that is produced is at 0. And of course, e to the, whatever number, 5 works. So we can definitely go up to positive infinity, and that will just keep moving that Poisson mean further and further and further out. And then as we move towards negative infinity, we'll be moving that Poisson mean closer and closer and closer to 0. So we stay in the legal limits for counts. All right, how does it work with probabilities? Well, the concept again, we take our linear model and we assign it to what is called the logit of some probability. Okay, so we have the probability of a success, for example, probability of survival, probability of passing a class, probability of making a purchase will be pi. And then probability of a failure is then 1 minus pi. So this logit function takes the log of this ratio that I have on the screen, right? It's just the log of this ratio. And that is what we assign our linear combination of alphas and betas and x's to. Now, in order to plug it into a Bernoulli or a binomial, if we have n, we do the inverse logit, which is a little bit more complicated, but recognize we just do the e to the power of the entire linear predictor, right? E to the power of the entire linear predictor over 1 plus e to the power of the entire linear predictor. And this way, no matter what the combination we get, no matter how close it is to negative infinity or infinity, what if it's 0? We always stay between 0 and 1 on this probability scale. So let's visualize that a little bit. Suppose we have a very simple model, just an intercept, and a slope with respect to a single x. So what we have is, of course, a line with respect to x. The question is, on what scale? For probabilities and proportions, it's linear, it's a line on the logit scale, right? Log of probability pi over 1 minus pi. And for the count, it's on the, well, log scale. So when we inverse link that, so when we transform it into the scale where we actually observe data, we can observe probabilities through taking relative frequencies, for example. We see that we are actually introducing ceiling effects and floor effects. So as our line continues progressing towards infinity, this logit function doesn't let us exceed 1. And as our line continues getting closer and closer to negative infinity, this function doesn't let us get below 0. Why? Well, remember that the inverse link function is e to the something over 1 plus e to the something. Suppose what we get inside of our linear predictor is a 0. All right, e to the 0 is 1. And then we get 1 plus e to the 0, which is 1. So you can see if what we get is a 0, on the linear predictor scale, we get a 0. It maps to 0.5, right? 1 over 2 is 0.5 on the probability scale. What if we get a really, really, really large number? All right, what if we get a really, really, really large number? Suppose it's infinity. Well, we have to be a little careful. We have to divide the numerator and the denominator by e to the infinity. And if we do this, we divide the numerator and the denominator by e to the infinity. We get 1 in the numerator, and then we get 1 over e to the infinity plus 1. So 1 over e to a very, very large number goes to 0. And we get 1 over 0 plus 1, so 1. So that's why we are introducing this ceiling effect when our linear predictor, or even x, approaches infinity. Our probability will just be approaching 1. And finally, the opposite happens. What if we get in the linear predictor, what if we get a very, very small number, like e to the negative infinity? All right, so same kind of thinking, divide the numerator and the denominator by e to the negative infinity. We get 1 in the numerator, we get 1 over e to the negative infinity plus 1. All right, so we have to be a little tricky. 1 over e to the negative infinity is just e to the positive infinity, which is a very, very large number. 1 over a very, very large number plus 1 goes to 0. And that means this line will just get closer and closer and closer to 0 without ever, ever touching 0. So that's how the logit and the inverse logit function works. That's why we don't have to worry about, if our variable values are too big or too small. We don't have to worry about, well, we do have to worry about priors, but not for the reasons that we're going to exceed 0 get below 0 or exceed 1. It's a little bit easier on the logarithmic scale. I've already showed you this. We can do, right, we just exponentiate. The inverse of the log is just the exponential. So the inverse of the log link is e to the power of. So if we get a really, really small number out here, e to the negative infinity goes to 0. If we get a 0, e to the 0 is exactly equal to 1, right? E to the 0 is exactly equal to 1. And e to the positive infinity, it of course blows up to infinity. So one thing to be careful about, we're used to sort of setting priors and keeping the scale of our observed data in mind. But it's hard because now we have to also think about 2 scales at once. We have to think about the probability scale and whatever scale you're setting your prior on, if you're using a normal distribution. then you have to worry about, well, if I take that normal distribution and I apply this transformation, then what is it going to induce on my probability scale? If I'm worrying about counts, I have to think about e to the power of. Priors that are really wide tend to blow up, right? If you start setting like normal, 0, even 100 priors, you said, oh, I just want to be uninformative. Well, you're going to end up having a non-trivial amount of data be e to the power of 100. And that just blows up. Look at how quickly this blows up. It blows up to infinity. You can have computational problems because you're feeding something that is a very, very large number into, say, a Poisson distribution. So we have to be really careful setting priors. And of course, I will show you an example in just a second. The other issue is the interpretation. When we had our linear model world, then beta was the expected change in y per unit change in x, holding all else constant. Now, because we transform, that interpretation only applies that expected unit change in y per unit change in x. That interpretation only applies on this scale. So here, beta is the expected unit change in the logit, on the logit scale per unit change in x. Here, beta is the expected unit change in the log, on the log scale per unit change in x. That's not how we want to report results. What the heck is a logit scale? It's a log of a ratio. That is hard to think about. So we have to modify our interpretations. So betas are the increase or decrease in the multiplicative odds of success, not the probability of success, in the odds of success. And when we go through that example, I'll show you why. And for the counts, it's the multiplicative effect on the risk or rate of an event. Right, so betas reflect now multiplicative changes on the odds of success if you're dealing with probabilities and proportions, or the rate or risk for an event if you're dealing with counts. Third reason why, there are 3 bullet points. I covered this one first, I covered this one second. I'm moving on to the third bullet point. In the linear world, in the linear model world, we had a separate old parameter that controlled variability, sigma. In the GLM, the Generalized Linear Model world, our mean and variance are set by the same parameter. Our mean and variance are defined by the model simultaneously. So for the Poisson, the mean is equal to the variance, equal to lambda. So the assumption with the Poisson is that as the mean increases, so does the variance. That's not a bad assumption, but oftentimes, as we will see, oftentimes, the variance is actually much bigger than the mean. And sometimes, more rarely, the variance is smaller than the mean. So we have to watch out. When we're modeling the mean, we're also implicitly modeling the variance. For the Bernoulli distribution, and a binomial, by the way, is just a product of n Bernoullis. So that's not a, the same thing that applies to a binomial. The variance is pi 1 minus pi. So if we have a model for pi, right, our pi is e to the power of something over 1 plus e to the power of something, we're not only changing the mean is then pi, but we're also changing the variance. So this can lead to some undesirable results if the mean and the variance are quite different. So stay tuned for that. These are just the difficulties as we're moving from the linear model world into a generalized linear model world. All right, let's start with Poisson GLMs. Poisson is applied to counts that are collected over some unit of space and or some unit of time. If we're counting COVID cases, then we don't want to just say there were 20 COVID cases. We want to say there were 20 COVID cases in a particular county over the last week, or in the United States over the last month. So there's very often some implicit or explicit population at risk. Now, there are counts that don't have population at risk, but then the counts are sort of occurring. Every observation, sort of implicitly has the same effort or the same population size from which it came from. So the COVID example I gave, the United States and a particular county clearly have different population sizes. 20 new COVID cases in a county and 20 new COVID cases for the entire country mean very different things. Sampling efforts are mostly what folks in ecology worry about. If you go out to find a particular species of bird and you send one graduate student into a particular area, they might come back with one count. If you send more graduate students or you spend more money or more time sampling the same space, you will come back with a very different count. So very often, we will want to apply what is called an offset. If you don't apply an offset, in my world, in public health, and a lot of social sciences, almost everything has an offset. Because if you're looking at a disease count, you're almost always asking how many people were eligible to contract this disease, whether the disease is cancer, COVID, or the flu. I am aware of a world where there are no offsets, but you are implicitly, assuming then that all of your observations come from equal, or at worst, very, very similar population sizes, or all of your observations came from very, same, or at worst, very similar sampling efforts. The fact that I can't come up with a plausible example to this shows you that I deal much more with this world where there is some number of people at risk and you are recording some count, from different communities. Every row is a different community, different county. Clearly, different counties in the US have very different population sizes, and so they are expected to have different counts. If you are applying an offset term, it appears here and here and here. You will notice that if it appears on the same side as all of your coefficients, the offset term is known. It doesn't have a coefficient. There's nothing to estimate for the offset. It's a known population. It's a known amount of sampling effort. And then your model simply modifies this known quantity in ways that are controlled by your covariates. So here are some ways to manipulate, the same equation. We start with our observed counts come from a Poisson distribution with some mean count. How is this mean count specified? Well, here I'm assuming that there is an offset term. So different rows in my data set, that's the i's, right? Different rows in my data set come from different communities where there were a different number of people at risk. There was a different sampling effort. And so it's included right there. And of course, look, we are applying the e to the power of inverse link function, right? So we want to specify our model in this scale, and then we exponentiate to put it on a typical count scale that is bounded by 0 below. But I can take the natural log of both sides, right? Take the natural log of both sides. Here is my linear model now. And I can even further rearrange and express that what we're actually modeling with our linear model is the log mean rate. On the left-hand side right there is the log mean rate. The influences of our covariates on the log mean rate. So, of course, if you just take all O's equal to 1, then arbitrarily we just get, you're assuming equal population sizes, same sampling effort, where of course all the O's disappear. And then you are modeling, here is your linear model on the right. You are then modeling just the mean count, not a rate anymore, no offset, just modeling the mean count. So let's take a look at an example that comes to us from public health. And in this example, I'm using smoking and all-cause mortality. All-cause mortality is just mortality due to any cause at all, not necessarily from smoking. And it comes to us from our neighbors up North Canada. So here, the rows of the data set, and I have it read into R, whoops. The rows of my data set have the number of dead folks recorded, what age category this was referring to, whether or not they smoked, and what was the eligible population that could have died. To make a rate, remember we're now modeling a log mean rate, I simply take the number of dead and divide by the population, and I get a rate. So 18 over 656, I get this 0.02. And of course, we think about a rate because 100 cases in New York and 100 cases in Laramie mean very, very different things. Another just very small note, when you're dealing with a complicated analysis, go ahead and change reference levels. So there's a smoking variable. As soon as I delete it, of course, I'm not going to use it. There's a smoking variable, no smoke, cigar pipe only, cigarette and something else, and cigarette only. Just go ahead and change the reference level. Change the reference level to something that is easy to interpret, because GLMs are hard enough. We know the interpretations, are multiplicative on this risk of an event scale. Don't make it harder for yourself than you need to. Change the reference level accordingly. So if I plot how the mortality rate on the y-axis changes as a function of age, right, here is my mortality rate, just number of dead over number of population. Here is my age, so it looks like it's people over 40. I suppose in this case, they felt they didn't need to study mortality rate for folks under 40. And I have a different line for those who didn't smoke, and then those who smoke different things. So as expected, we see that we have increasing mortality with age. So in public health, by the way, when you're dealing with just about any kind of death or disease, you must account for age. Age is a very important variable that is simply essential, to where if you don't account for age, the analysis might actually be invalid. So that's why I have a different line for the smoking status and also adjusted for age. It looks like the orange line, salmon line, is below the others. And that would indicate, this is an exploratory graphic, of course, this would indicate that those who didn't smoke die at a lower rate when adjusted for age than those who did smoke. So the next thing we're going to do is practice setting priors. So we set priors on this linear model scale. So again, notice that you can either step down by taking logs, or you can step up by exponentiating, and you're going to get to exactly the same point. But I like to start here because this is where we set our priors. We set our priors to each individual parameter. And so it's useful to start at the scale at which we set our priors. We take the e to the power of both sides, right? The log disappears, and we now have this e to the power of situation right there. Finally, I can divide both sides by population and show that here is my rate, mortality rate, and here is my sort of fitted line. So when we do our prior predictive simulation, I want to compare those two sets of priors. So first of all, why would, notice that I'll be using a centered and scaled age. This is centered and scaled age. And if I'm centering and scaling age, then this alpha is just represents the mean. But the mean of what? The mean of the log mean rate, right? If I move this over to this side, I'm going to get the log lambda over the population, which is the log mean rate. What is the log mean rate for my data set? Well, I can do this. So my observed mean is 0.2. That's for my observed mean rate. My observed median is 0.16. So I'm going to go ahead and set it somewhere in between. I'm modeling the log mean rate. So I'm going to set that prior mean to be somewhere between -1.6 and -1.8. I'm going to just go ahead and set it the prior mean for my alpha, the intercept, to be somewhere between the mean and the median. In this case, -1.7. That's how I got -1.7. This standard deviation, 2.5 is standard in a lot of analyses that I've noticed. And I just want to show you that if you apply things that are standard kind of blindly to your data set, it might be standard in that it applies to 80% of the data sets out there, but it's not going to apply to this one. The prior for the betas is a little bit less controversial. Remember, if we center and scale, it makes sense to set our prior mean to be 0. We're not a priori assuming a positive or a negative effect, although if there was ever a time to assume a positive and negative effect, it would be with age and mortality. There's no way that as age increases, mortality would decrease. But just, you know, how things are typically considered and published in the literature, if you're using a centered and scaled variable, your beta coefficients are usually going to be normally distributed, centered around no effect, which is 0, with some hyper standard deviation. So let's see what this produces. You know, on first glance, these are quite narrow priors. You know, you think about the coefficient of variation. You think about, you know, things we know about the normal distribution. These are quite narrow at first glance. As per usual, I'm going to make my plot, empty plot. So I've got my age right there. I've got my mortality rate. Notice that I'm using the twice the observed mortality rate to set my lower bound and sort of, you know, maybe call it plausible upper bound. So we've always set it as being arbitrarily larger than the observed range of the outcome variable. And maybe disregard my label, because the label was for the PowerPoint presentation. So this label should be, I'll just adjust the label. No problem. Then 500 times, I'm doing e to the power of my linear predictor. Notice I'm doing e to the power of alpha plus beta times a centered and scaled age. In the notes, I started by setting my priors on this log scale. Then I had to transform things into a rate because each count came from a different population at risk. And on the right-hand side, yeah, you see there's e to the power of alpha plus beta age times a centered and scaled age. All right, let's take a look at what that produces. And it produces mayhem. Mayhem. This is garbage. Remember, we've set this bar to be twice the observed range of data as is. All right, we don't want to set our priors for what we observed. We want to set our priors for the world that produced our exact data set. So this is just mayhem. I can't tell what's going on. Look, you can tell there are some lines that are headed up. There are some lines that are headed down. There's some going on over here. It looks like blue seaweed, frankly. So let me just cut to the chase. What if you say, all right, that was too large? Maybe you wouldn't cut it to 0.5 right away. But if you do cut it to 0.5, if you do cut it to 0.5, a lot more reasonable. We still have these lines that start low and go high. We have lines that start high and go low. Maybe you will argue with me that maybe I should have increased this to make sure that I didn't have a lot of these lines where the mortality rate for younger ages is actually higher than the mortality rate at older ages. Maybe we should have had something like this. If there was ever a time, it would be with age and mortality. All right, so now there's more lines that have an increasing rate than lines that have a decreasing rate. But this looks a lot more reasonable. You would probably even reduce it a little further. But at that point, I get a little antsy if we start setting priors that are too narrow. All right, so that right there is pretty darn narrow. Notice that we're assuming a fairly flat effect of age. Only very few of the lines deviate from this cluster down here. So that's why I went with 0 here, 0.5 here, 0.5 here, and negative 1.7 here, and again, negative 1.7. If we take a look at our mean rate, we take a look at our median rate, and we take a look at the log of that quantity, because that's what we're modeling, log mean rates. We see that in this case, that for some reason didn't work out. But if you take the log of 0.2 and a log of, I think, 0.16, I set my prior mean to be in between those logs right there. Okay. So that's how we set our priors. So we have to be a lot more careful. On the exponential scale, things really blow up quickly. So let's finish out this lecture by fitting our first Bayesian generalized linear model. I'll be using the BRMS package. A couple of things to keep in mind. So first of all, I always used to forget, and might still do, why you go offset. When you say offset, you are telling R not to estimate a coefficient for this term. We're going to estimate a coefficient for this term, but we're not going to estimate a coefficient for that term. We know the population. There's nothing to estimate there. And it's log population. All right, this matches up. Log population plus a linear combination of other parameters. That's why we have the log population inside of our offset function there. Here are our priors. We just discussed those. So notice that we don't have a sigma prior anymore because the Poisson distribution doesn't have a sigma, right? We just have the prior distribution for the intercept and a prior distribution for my 1 beta coefficient. The rest of this stuff looks very, very similar to what we're used to, except for now my family is Poisson. So I'm going to run this model, and what I get is this. The output reminds us what we set our GLM family to be. The output reminds us that the link function was log, and that means the inverse link function, the one that maps it from our model scale, inverse link, maps it from the model scale to the data scale. The inverse link to a log is then the exponential, okay? Here is the formula and what we treated as an offset. We only have 36 observations, by the way, but that's because, you know, the deaths were aggregated. And for now, we don't have smoking. We'll deal with that next time. So here are my estimates. But remember, I'm not saying that my mean count is negative 1.79. This is on the log scale. I'm not saying that per standard deviation of age, my deaths increase by 0.8. None of that, right? We need to interpret our coefficients carefully. And in this case, remember that we need to exponentiate it. So what we say is our mortality rates, right? I can rearrange this to put lambda over the population of the right on the right-hand side. And this is a rate. So our mortality rates increase by e to the power of 0.8. That's the coefficient, which is 2.2 times per standard deviation increase in age. Why standard deviation? Because I have a z of age in the model. The standard deviation of age for this data set is about 12 years. So what are we saying? Mortality rates about double per about 12 years. Right? So rates double per 12 years, every 12 years. And of course, as expected, you know, very significant result. 0 is nowhere inside the credible interval, as expected. Age is a super important predictor of mortality. If I look at what the WAIC produces, some interesting things. Yeah, you get the WAIC. As a reminder, it's not interpretable in itself. 593 is nothing. It's only interpretable in a comparative sense. The effective number of parameters is interpretable. But you know what it means in GLMs is a measure of model complexity. And therefore, it too is comparative. Because 21.5 doesn't correspond at all to the two things you're actually trying to estimate. You were trying to estimate alpha, the intercept, and beta, the slope with respect to centered and scale age. The model returns an effective number of parameters of 21.5. But this, in generalized linear models, becomes a measure of model complexity. And so it too becomes comparative. Right? Plenty of new material. Let me pause here. We'll kind of keep working with the Poisson next time when we introduce smoking into the equation. Guys, stay safe, stay sane, and I will talk to you later. Bye-bye.